Imagine spending, I don't know, $40,000 on the absolute fastest, most advanced AI GPU on the planet.
Okay.
You install it, you power it up, and then you just watch it sit there, totally idle, just doing absolutely nothing. And why? Because it's waiting on a $2,000 computer chip to hand it an instruction.
I mean, that is the ultimate data center nightmare.
Right.
And honestly, it happens way more often than people realize. It's basically because of a fundamental misunderstanding of how these systems are actually put together.
Yeah, because whenever you read headlines about, massive artificial intelligence breakthroughs, all the glory goes to one place. It all goes to the GPUs.
Always.
They're the rock stars. They're the heavy lifters, right?
Right.
The raw, unfiltered muscle behind every single generative image you create or every chatbot prompt you send. But here's the thing about muscles. They are completely, utterly useless without a central nervous system to tell them what to do.
Exactly. And that nervous system, the orchestrator behind all that raw mathematical power, is the central processing unit, the CPU.
The unsung hero.
Completely unsung. Because the GPUs are doing all the highly publicized math, the CPU in an AI supercomputer gets, well, almost entirely ignored by the public. But if you actually look at the engineering, the CPU is the bottleneck that dictates literally everything else.
Which is exactly why we are turning our attention to it today.
Yeah.
For this deep dive, you and I are going to unpack a really fascinating stack of technical architecture notes. We've got system specs detailing the entire evolution of NVIDIA's famous DGX AI supercomputers.
And I have to say, these documents are like a masterclass in system design. We aren't just looking at a parts list here.
No, definitely not.
We're looking at essentially a 10-year war against the laws of physics, just engineers trying to keep the flow of data moving fast enough to keep those GPUs fed.
Yeah, so we're going to trace this hidden evolution of the CPU inside these million-dollar machines. We'll look at how they started with standard Intel models, made a massive pivot to AMD, went back to Intel, and that.
Well, then they basically tore up the entire rule book.
Right. They made this radical decision to build a custom ARM architecture entirely from scratch.
Which is fascinating, and understanding that shift really gives you a much better grasp of how AI actually works at a physical hardware level.
For sure.
Because it's a story driven entirely by causality. As the GPUs got hungrier, the physics of the motherboard just began to break down.
Okay, but before we get into the specific silicon, I feel like we need to establish the baseline. If you are building a box with 8 massive NVIDIA GPUs in it, what is the CPU even doing?
That's the perfect place to start.
Let me try to frame it like this. Imagine a high-end restaurant kitchen on a Friday night.
Okay, I'm with you.
The GPUs are your incredibly fast, highly specialized line cooks. They're furiously chopping vegetables, searing steaks, plating dishes at lightning speed.
Yeah.
Those are your CUDA operations, right?
Mm.
The parallel processing that GPUs are just amazing at. But the CPU. The CPU is the expediter standing at the front of the kitchen.
Oh, I like that. Taking the tickets, calling out the orders.
Right. Taking the tickets from the waiters. The CPU figures out which station needs to do what, fetches the rare ingredients from the walk-in freezer, and, make sure the final plates actually make it out to the dining room in the right order.
Yeah.
If you have the greatest line cooks in the world, but your expediter is slow,
Yeah.
your cooks are just standing around twiddling their knives.
That is a remarkably accurate analogy. Let's actually apply that to the source text, because the architecture notes map out 3 non-negotiable jobs for the CPU in a DGX system.
Okay, let's hear them.
So the first is data ingestion, grabbing the ingredients from the freezer, like you said. But we aren't talking about a few carrots here. We're talking about pulling astronomical amounts of training data from NVMe storage.
Which is essentially the ultra-fast enterprise flash memory used in modern servers, right?
Exactly. But it's not just moving the data. It has to prep it. It has to decompress it.
Oh, because the files are so big.
Right. AI training data sets are so massive they have to be heavily compressed just to fit on the storage drives. And a GTU is honestly terrible at decompression.
It just wants to do the math.
Right. It wants to do matrix multiplication.
Yeah.
So the CPU has to run the algorithms to unpack those massive zip files on the fly and stream the raw data into the GPU's memory. If the CPU can't unpack the data fast enough, the GPU starves.
Wow. Okay, so that's ingestion. What's the second job?
Network management. A single DGX machine doesn't train a massive frontier model by itself. It works in a cluster of thousands of other machines.
Like a giant hive mind.
Yeah. So the CPU orchestrates the massive traffic flowing across the network fabrics, whether that's InfiniBand or, 400 gigabit Ethernet. It handles all the packet routing overhead.
Making sure nodes are talking to each other properly.
Exactly. Ensuring that this node can synchronize its math with a node halfway across the data center without skipping a single beat.
Which sounds like an absolute logistical nightmare.
Right.
What is the third job then?
Managing the non-accelerated tasks. So the DGX system actually runs an operating system, the Ubuntu-based DGX OS. And beyond just keeping the system running, as AI moves toward agentic workflows, where the AI is using tools, running Python scripts, querying web APIs.
Doing step-by-step logic stuff.
Yeah, exactly. The CPU has to manage the logic of those tools. Those sequential step-by-step scripts are not optimized for the highly parallel CUDA architecture of a GPU. The CPU has to step in and handle them.
Okay, let's unpack this. If the CPU has to manage all this data unpacking, all this chaotic networking traffic, and the entire operating system, how do system designers even keep up? I mean, you can't just drop a standard desktop processor in there and hope for the best.
You really can't. Though if we look at the early days outlined in the specifications, they did start with very high-end but relatively standard x86 architectures.
Like the Intel Xeons.
Yep. In the DGX1, which was powering the early Pascal and Volta generation GPUs, NVIDIA used dual Intel Xeon E5-2698 V4 chips.
Just standard, reliable data center workhorses.
Reliable and very well understood by developers. And they followed that up in the DGX2 with dual Intel Xeon Platinum 8168 processors that fed 16 Volta GPUs. At this point, the Intel x86 architecture was just the absolute standard. The entire software ecosystem was built around it, and it could handle the data ingestion needs of the time, mostly because the GPUs themselves weren't moving data fast enough to break the system yet.
But then, looking at the source notes, there's a massive fracture in that dynamic. We enter the Ampere era with the DGX A100, and suddenly Intel is out.
Completely out.
NVIDIA pivots hard to AMD. Specifically, dual AMD EPYC 7742 processors, the Rome generation chips. So what changed? Why throw out the Intel standard?
Well, AMD brought two critical hardware advantages to the table that Intel just didn't have ready at that exact moment. First, AMD led the market in PCIe Gen 4 support.
And we should clarify for everyone, PCIe is the physical interface, right?
Yeah.
The literal copper lanes on the motherboard that connect the CPU to the GPUs and the network cards.
Right. And moving to Gen 4 doubled the physical bandwidth of those lanes. The pipe basically got twice as wide.
Okay, that makes sense.
But the second reason for the AMD pivot is what really highlights the changing nature of AI. It was sheer core density. By using those two AMD EPYC processors, the DGX A100 system had 128 CPU cores dedicated solely to managing the system.
Okay, wait, hold on. 128 cores just for background management.
Yep.
My laptop has 8 cores, and it can edit 4K video while running a dozen applications. We're talking at 128 cores acting purely as an expediter. That feels like a massive waste of silicon. Why on earth did they need that much density just to feed the GPUs?
I know, it sounds absurd. Until you look at what AI models actually started doing during the Ampere era, the source text points directly to the rise of massive RAG, retrieval augmented generation.
Right, and to be clear for you listening, RAG is when an AI model doesn't just rely on its internal training. It actively goes out and searches a massive external database or a huge library of documents to pull relevant facts before it generates an answer.
And mechanically speaking, RAG is a nightmare for a processor. Oh yeah, matrix multiplication, the stuff GPUs do, is incredibly predictable. It's heavy, sure, but it's an orderly march of numbers. ARG, on the other hand, requires thousands of tiny, unpredictable, chaotic parallel input and output requests.
Just constantly searching and grabbing random data.
Exactly. The system is constantly jumping around, running vector database lookups, retrieving disparate chunks of text, formatting them.
So it's not about raw power, it's about thread count. It's about how many separate chaotic tasks you can juggle simultaneously.
You hit the nail on the head. If you tried to push that level of chaotic data shuffling through a standard CPU with only 24, 32 cores, the I/O queues would just fill up immediately.
It would bottleneck.
The CPU would hit 100% utilization just trying to manage the search queries. It would choke. And when the expediter chokes, the line cooks stop cooking.
Wow.
AMD's 128-core architecture provided that massive parallel overhead required to ensure the CPU never became the bottleneck during complex retrieval tasks.
Okay, so AMD solved the lane width problem with Gen 4, and they solved the threading problem with 128 cores. The kitchen is humming again. But then, as we move further into the architecture notes, the pendulum swings right back.
It does.
We hit the modern era. The absolute powerhouse is making headlines right now. The DGX H100, which uses 8 Hopper GPUs, and the brand new DGX B200, which uses 8 Blackwell GPUs. And for these systems, NVIDIA went back to Intel.
They did. For the H100, the specifications show two 4th-gen Xeon Platinum 8480C chips. For the B200, it's two 5th-gen Xeon 8570 chips.
Let me guess. The Hopper and Blackwell GPUs got so ridiculously fast that even AMD's 128 cores in Gen 4 lanes just weren't enough anymore.
Well, that's half the picture. The GPUs did get faster, but the real breaking point was actually the network. The driving force here was PCIe Gen 5.
Oh, Gen 5.
Yeah, Intel managed to bring robust Gen 5 support to the data center exactly when NVIDIA was designing these new systems.
And this was because the network adapters got too fast.
Exactly. Look at the Connect X7 and Connect X8 network adapters listed in the specs. The DGX box has to ingest and export so much data to the rest of the data center that the network traffic alone was saturating the motherboard's lanes.
So they needed a bigger pipe again.
They needed the massive throughput of Gen 5 just to keep the system communicating with the outside world.
You know, I think this is the perfect time to really visualize this PCIe connection because honestly, it's the central villain of this entire story. The motherboard itself is the enemy here.
It really is.
Let's expand our analogy. Let's imagine the CPU and its memory as one bustling city, and the GPU and its memory as a completely separate city across a river.
Okay, let's push that analogy a bit further. The PCIe bus, whether it is Gen 4 or Gen 5, is a toll bridge connecting those two separate cities.
Right. Now, Gen 5 is an incredibly wide, incredibly fast state-of-the-art bridge. It's a marvel of engineering. But at the end of the day, it is still a toll bridge. Every single piece of data, every parameter of the AI model, every training image has to stop at the toll booth.
It has to pay a PCIe tax.
Exactly.
Yeah.
And that tax is paid in latency and power. You are physically taking data from the CPU's memory, pushing electrons across inches of copper traces on a motherboard, and depositing that data into the GPU's memory.
And if we connect this to the bigger picture, you've just identified the fundamental flaw of the entire historical architecture.
Yeah.
As long as you rely on third-party x86 chips, whether from Intel or AMD, sitting in standard motherboard sockets, you are operating two separate cities. You will always have to pay that memory copy tax.
Which has to be incredibly inefficient.
It takes an immense amount of electricity. When an AI model scales to hundreds of billions or even trillions of parameters, the power and time spent just physically shuttling electrons across that toll bridge becomes an astronomical drag on the entire system.
Generates heat, it eats up kilowatts of power, and it creates a hard ceiling on your speed.
Absolutely.
Which brings us to the ultimate paradigm shift in these source documents. Because if your toll bridge is fundamentally flawed because it forces you to copy data back and forth, how do you solve it?
You tear down the bridge.
Exactly. You tear down the bridge completely, and you merge the two cities into one giant metropolis.
This is the in-house shift. NVIDIA looked at the physics of the motherboard and realized that buying off-the-shelf x86 components, no matter how advanced Intel or AMD made them, was no longer viable for their absolute highest-end designs.
The physical distance was just too much.
The physical distance and the PCIe protocol itself were the bottlenecks.
Enter the NVIDIA Grace CPU. You find this in the DGX GH200. Which, by the way, pairs an insane 256 Hopper GPUs together, and the DGX Station Blackwell. Instead of buying from Intel or AMD, NVIDIA built their very first data center CPU themselves.
And they abandoned the x86 architecture entirely to do it. The Grace CPU is built on the ARM v9 architecture. Specifically, it uses 72 ARM Neoverse v2 cores.
ARM processors are usually known for power efficiency, right? Like, that's what runs in your smartphone.
Yeah, they are highly power efficient, which definitely helps when you're trying to cool a massive supercomputer. But the real reason for building their own ARM chip wasn't just power.
What was it?
It was control. By designing the silicon themselves, they controlled exactly how the CPU talks to the GPU. They threw out the PCIe standard altogether for this connection.
But they bypassed the motherboard entirely.
Essentially, yes. They use their own custom interconnect called NVLink-C2C. That stands for chip-to-chip. And the bandwidth numbers here are just staggering. NVLink-C2C provides 900 gigabytes per second of bandwidth between the CPU and the GPU.
Here's where it gets really interesting, just to help you visualize that. 900 gigabytes per second is like transferring hundreds of full-length, uncompressed 4K movies between the processor and the graphics card every single second.
It is 7 times faster than standard PCIe Gen 5. 7 times the bandwidth of the fastest standard highway available on a normal motherboard.
So the expediter and the line cooks aren't just in the same kitchen anymore, they're practically sharing the same nervous system.
Very much so.
But the sheer speed is only half the magic, right? The source text highlights a concept here that basically completely rewrites how AI models are programmed.
Yes. It is arguably the most crucial technical revelation of this entire deep dive. Unified memory.
Okay, explain that.
Because of that massive 900 gigabyte per second NVLink connection, the CPU and the GPU no longer have separate, isolated memory pools. They share a single, coherent memory space.
The two cities are officially merged into one.
Exactly. From a software perspective, the CPU can look at a piece of data residing in the GPU's memory, and the GPU can look at data residing in the CPU's memory directly.
No copy.
No copying. They don't have to pack it up, put it on the PCIe bus, and copy it over to the other side. They just pass a pointer, they point to the memory address and say, the data's right here, go work on it. The dreaded PCIe copy tax is completely eliminated.
That is just wild. Think about the mechanical efficiency gains there. If you don't have to spend electricity and time physically duplicating petabytes of data just so the other processor can look at it, you suddenly free up a massive amount of system resources.
Massively.
You lower the thermal output, you drop the power consumption, and the speed just skyrockets.
It fundamentally changes how AI models can ingest and process data. Think about the older setups. If an AI model was larger than the memory physically located on the GPUs, which happens all the time with these new trillion parameter models, you had to aggressively manage swapping data back and forth from the CPU's system memory over that PCIe toll bridge.
Which sounds like a nightmare to code.
It was incredibly complex to program, and it was slow.
But with Grace.
With the Grace architecture and unified memory, the GPU has direct high-speed access to the massive pool of memory attached to the CPU. It treats the entire system's memory as its own personal playground.
So the programmer just dumps it all in.
Right. The programmer doesn't have to write complex code to shuttle data around. They just load it into the unified pool and let the silicon handle it.
It's brilliant. It's taking the wall down between the expediter and the line cooks. They're operating from the exact same counter now. No shouting orders across the room, no running physical tickets back and forth, just immediate shared access to everything.
And it speaks to the harsh reality of where AI hardware is going. The limiting factor in artificial intelligence is no longer just how fast you can do the math.
The math is solved.
The math is highly optimized. The limiting factor is the physical movement of electrons. It's how fast you can move the data to the processor doing the math. By designing the CPU themselves, NVIDIA ensured that the flow of data is perfectly physically harmonized with their GPUs.
Which is a perfect way to summarize this incredible decade-long journey we've just been on. When we look back at the whole picture, it is amazing how much the CPU's role, this completely unsung expediter, dictated the design of the most famous supercomputers on Earth.
It really did.
We started with the early days, relying on the solid foundation of standard Intel architectures. Then, as AI models evolved to demand insane retrieval and chaotic data shuffling, the physical system had to pivot. They chased AMD's massive core density to handle the thread counts.
Which then led to maxing out the lane bandwidth of Intel's PCIe Gen 5, just to handle the incredible data volumes being pushed by the new network adapters.
Right. And finally, when the physics of standard motherboards and the sheer electrical cost of those toll bridges became too much of a burden, they literally tore up the rulebook. They built a custom ARM CPU with the Grace architecture, utilizing NVLink to physically merge the memory pools and erase the copying bottleneck once and for all.
It is a profound structural evolution. It shows that in the data center, no component operates in a vacuum. The greatest, most expensive GPU in the world is forever held hostage by the slowest data lane connected to it.
So what does this all mean for you? Well, the next time you open up a browser window, type a complex prompt into an AI tool and get an answer back in the blink of an eye. Take a second to appreciate the sheer mechanical choreography that just happened behind the scenes. Yes, the GPUs crunched the heavy numbers.
Absolutely.
But there was an unsung hero, an expediter, that had to rapidly pull the data from flash storage, run the decompression algorithms, orchestrate the network traffic across thousands of nodes, manage the system tools, and flawlessly feed those hungry GPUs without dropping a single ticket. The CPU made that lightning-fast answer possible.
This raises an important question, though, a final thought to consider as you look at where this technology is heading.
What's that?
Building on this revelation of unified memory and the incredibly fast NVLink connection, if custom interconnects are allowing CPUs and GPUs to share a single memory pool and function almost as one cohesive brain, are we approaching a future where the physical and architectural lines between the CPU and the GPU vanish completely? Are we moving toward a reality where we no longer have a separate expediter and line cook, leaving us with just one single unified AI processor.
Because if the muscle and the brain merge into the exact same piece of silicon, well, that changes the rules of artificial intelligence